All right, let's dive right in. Today we're tackling a real classic, problem 1.67 from Irodov's legendary physics textbook. This is one of those fantastic problems that really gets you thinking about forces, friction, and even a little bit of calculus to find a really elegant answer. So let's get started.
So think about this for a second. Let's say you're trying to drag some heavy box up a ramp. You've got a rope. Now, what's the smartest way to pull it? Do you pull straight, kind of parallel to the ramp? Or is it better to pull up at an angle? Which way is actually going to make your life easier and require the least amount of muscle? It's a really practical question, right? And today, physics is going to give us the one single, definitive answer. And to find that answer, we're going to dig into Irodov's problem 1.67. We're going to break it down piece by piece. The whole goal here is to figure out that exact angle that minimizes the force you have to apply.
Okay, first things first. Section 1, the setup. Before we can solve anything, we've got to know exactly what the problem is giving us and what it's asking for. Let's lay it all out.
So here's what we're working with. The problem gives us three things: the mass of the object, which we'll call m, the angle of the ramp, that's alpha, and the coefficient of friction, which is k. Simple enough. And our mission? We need to find the perfect angle for our pull. We'll call that beta. That makes the tension, T, in the rope as small as it can possibly be. Now, here's the tricky part, the real challenge. Both the tension and the friction are connected to that angle beta. They change together. So we're looking for that perfect sweet spot where everything balances out just right. All right, on to section 2, mapping the forces. To really solve this thing, we've got to visualize every single force acting on this block. Let's get everything down on paper.
Now, if you take away one thing from any mechanics problem, let it be this. Your number one tool, your absolute best friend, is a good, clear, free body diagram. It is the most important step, period. And hey, here's our pro tip for you. We're going to tilt our coordinate system. Instead of the usual flat X and Y, we'll line up our X-axis with the ramp itself. Trust me, this little trick is going to make the math so much easier to handle.
Okay, let's build this thing together, step by step. First up, we just draw our block on that inclined plane with our new tilted axes. Easy. Next, let's put in gravity. Remember, gravity always pulls straight down, so our mg vector points to the center of the Earth. We'll break that down into two pieces, the part pulling it down the ramp, which is mg sine alpha, and the part pushing it into the ramp, mg cosine alpha. Okay, what's next? The normal force, N. That's just the ramp pushing back, and it's always perpendicular to the surface. Then we add our own force, the tension, T, pulling at that angle beta. We'll split that one up too. T cos theta is the part actually pulling it up the ramp, and T sine theta is lifting it a bit. And last but not least, friction. The force of kinetic friction, F sub k, always fights the motion, so it's pointing back down the ramp. And boom, that's it. That's our complete map of every force in play. Section 3, applying Newton's second law. We have our picture. Now it's time to turn that picture into math. Let's write down the equations. So let's look at our two directions. First, the y direction, perpendicular to the ramp. The block isn't jumping up into the air, and it's not falling through the wood, right? So all the forces in that direction have to cancel out. They sum to 0. The upward forces, that's the normal force plus the upward bit of our tension, have to perfectly balance the downward component of gravity. Now for the x direction, along the ramp. We're looking for the minimum force needed to pull it. That means we're just about to get it moving, or we're moving it at a constant speed. Either way, acceleration is 0. So again, the forces have to balance. The forward pull has to be exactly equal to the forces dragging it back. That's friction and the downhill part of gravity. Okay, pause. This is super important. This is the number one mistake people make with this kind of problem. You might be tempted to just say the normal force is mg cos alpha, like it is in simpler problems. But no. Look at our diagram. Part of your pull, that T sine of beta component, is lifting the block off the ramp a little bit. Because you're helping to lift it, the ramp doesn't have to push back as hard, so the normal force gets smaller. And since friction depends on the normal force, you see where this is going? This is the absolute key to solving the whole thing. Okay, section 4, finding the minimum tension. We've got our equations set up. Now for the fun part. Let's do some algebra and a tiny bit of calculus to hunt for that minimum force. So what's our game plan here? It's actually pretty straightforward. We need to get one single equation that has tension, T, on one side, and everything else, including our angle beta, on the other. We want to see exactly how T depends on beta. Let's just walk through the steps. From our y direction equation, we can solve for the normal force, N. And you can see right there, it's mg cos alpha times minus T sine beta, just like we talked about. Now we know friction is just K times that normal force. So we're going to take that whole big expression for N and plug it right into our x direction equation. Now it gets a little messy, but it's just algebra. We just have to rearrange things to get all the terms with T on one side, and there it is. We have our master equation. This formula tells us the tension for any angle beta we choose. So how do we find the minimum value from that big equation? Well, this is where calculus comes in to save the day. Think about any curve. The very bottom point, the minimum, is the one spot where the curve is perfectly flat, right? The slope is 0. And the tool we use to find the slope of a function is the derivative. So to find the minimum, we just need to find where the derivative is 0. Now, let's look at our big tension formula again. See the top part, the numerator? Everything in there, m, g, alpha, k, it's all just a constant number. It doesn't change. The only thing that does change is the bottom part, the denominator, because it has our angle beta in it. So here's the clever insight. If you want to make a fraction as small as possible, what do? You make the bottom number as big as possible. So our problem just changed. Instead of minimizing t, we just need to maximize the denominator, d. So let's do it. Let's take the derivative of that denominator with respect to our angle, beta. It's a pretty standard derivative. The derivative of cosine is negative sine, and the derivative of sine is just cosine. So there's our result. And now for the magic step. We take that derivative we just found, and we set it equal to 0. This is how we find that one specific angle where the denominator is biggest, which means our tension is the smallest. Okay, section 5, what the answer means. We've crunched the numbers, but an equation is just symbols on a page until we understand what it's telling us. So let's figure out what this result actually means in the real world.
So let's just rearrange that last equation. We can just move the sine of beta to the other side. That gives us k times cosine beta equals sine beta. Now, if we just divide both sides by cosine beta, what do we get? Sine over cosine is tangent, and we get this. Tangent of beta equals k. I mean, how simple and elegant is that? All that work, and it boils down to this beautiful little relationship. The best angle to pull at is simply the one whose tangent is the coefficient of friction. And this is where it gets even cooler, because this connects to a really neat physical idea. That number k, the coefficient of friction, it's not just some random value. It's actually defined as the tangent of something called the angle of friction. So what our answer is really telling us is that the optimal pulling angle beta is literally equal to the angle of friction, phi. The math reveals a deep physical truth. That's just awesome. So let's just step back and think about why this is the answer. It all comes down to a trade-off. On one hand, as you pull up at a steeper angle, you're lifting the block more. That's good. It reduces the normal force, and that slashes the amount of friction you're fighting. But on the other hand, the steeper you pull, the less of your effort is actually going into pulling the block forward up the ramp. See the conflict? Our answer, tan beta equals k, that's the absolute perfect balance point. It's the angle where you get the most benefit for reducing friction without losing too much of your forward pulling force. And just to close the loop, if you take our optimal angle and plug it back into that big master equation for tension we found earlier, you get this. This is the formula for the absolute minimum tension you'll ever need to exert. It's the final answer to the problem, the lowest possible force required. So there you have it. But, a good physicist never just accepts an answer. They test it. They push it to the limits to see if it still makes sense. So here's a question for you. What if there was no friction? What if the surface was perfectly slippery and k was 0? What does our formula, tangent beta equals k, tell us the best angle would be then? And more importantly, does that answer make physical sense? Give it some thought. It's a great way to really check if you've understood the physics behind the formula.